In this lesson we talk about trees and ensembles. So first let's have a look at our cartography of the methods we are seeing in this course. So we have already seen linear regression and polynomial regression. We have done classification with logistic regression and also with neural networks. Now today we will focus on tree-based learning to do classification, and in next lesson we will use it also to do anomaly detection. So tree-based learning is an idea completely different from the methods we have seen so far. It is based on a certain graph, and in particular a tree, and it works like a pinball machine in some way. So you have your sample, you let it fall into this tree, and it will arrive at a certain leaf of the tree. You will assign to the sample the label correspondent to that leaf, and we will see what it means in practice. So today I will first introduce the structure of decision tree. Then I will introduce an algorithm called CART used to train a decision tree, and we will see the metrics that it uses to do so. Then we will observe that trees suffer high variance. They are very unstable. So to fix this problem, we will assemble different trees together to form an ensemble. Okay, and we will use, so to make any prediction, all the set of different trees. And we have different methods to do so: bugging, random forest, or extra trees. We will also see that trees are nice because they provide a high interpretability, in the sense that we can have an idea of a confidence that we can have in the results they give us, and also of the features that are the most important. So, before talking about decision trees, let me introduce a use case that I will use in these first slides, that is about a smartphone application called Future Mobility Sensing. The goal of this smartphone is to collect from your phone data like gyrometers, accelerometers, GPS data, connection information, etc. And the final goal is to infer your mobility, and in particular the type of activity you are performing, if you are home or if you are at work, for instance. Why it is important? Because suppose you are an authority, a transportation authority, and you want to understand whether it's worth spending money to construct a new bridge or to introduce a new service, let's say autonomous taxi services. So you want to understand before spending money if the users will adopt this new service or this new bridge, if they will use it. If not, it's better not to spend this money directly. So to do so, you need to create a model of your users. You need to understand what they do, where they live, and where they work, and at which time they make their movements. So either you go to each user and you ask to answer a set of questions, which is costly and time consuming, or you may ask to a subset of users to install an application that will automatically detect their kind of activities without their intervention. This is what this application is meant for, and it is used for research projects and also for actual authority projects of authorities around the world. Okay, so with this use case in mind, let's talk about a decision tree. So a decision tree is a graph, and in particular it is a tree that looks like this. So it has a set of nodes, and each node is characterized by a splitting rule that looks something like this. So these are the, I forgot to tell you what are the features of our datasets. Okay, they are data from the phone, accelerometers, gyrometers, GPS, movement, etc., and also the characteristics, the profile of the individual, its age, his sex, etc., and also the time at which you perform the measurements. So in a decision tree, a splitting rule is something like this: age less than 80, time less than 8 a.m., etc. So some of each node, each terminal node, so the leaves, are labeled with a certain activity, either home or work, which is what we want to infer. And so when you want to infer the class of a new sample, you take the sample and you let it cross this tree. So for instance, let's take this sample here, age 50, time 10 a.m., etc., and let's see where it falls. So age 50. So age 50 is less than 80, so the sample goes here. Time, our time is 10 a.m. So 10 a.m. is more than 8 a.m., so it goes here. Duration is 7 hours, so the sample goes here, and phone use is 2%, so the sample goes here. So we will classify this sample as work. Okay, this is why a random decision tree looks like a pinball machine. You have a sample and you let it fall until it reaches one of the leaf. In this case, it reached a leaf labeled as work. Okay, so observe that each split corresponds to a partition of the feature space. So let's consider, for simplicity, just two features, time and age. When we are at the root node, this root node contains the entire feature space. Okay, then after we apply the first splitting rule, we are actually dividing the feature space in two regions. This region here that corresponds to all the samples that pass by the node N2. And this region here with age more than 80, which corresponds to this node. Then, if we apply another splitting rule here, time less than 8 a.m., it means that all the samples that are less than 8 a.m. will be represented by this region. All the other samples are represented by this other region. So there is a dependency between the nodes of our tree and the regions of our feature space. So observe then that all the samples in region N6 will be classified as, suppose, home, and the samples in N5, suppose it has been labeled with work. So this is work, this is home. So observe then that we are dividing the region, and in each region we have one specific class. So in other words, these lines here are representing the decision boundaries. So that are the lines at which our classification changes from home to work, for instance. Or if N3 is home, this decision boundary changes from work to home. Okay? And we can immediately see that our decision boundary is not linear. So we have seen with logistic regression that the decision boundary there is linear. So this is a limitation of logistic regression. While here we can already classify problems that are more difficult. Problems in which all the home samples are in here, and the work samples are here. Okay. So a decision tree is a non-linear classifier. So, so far we have assumed that we have received our tree ready to use, with all the splitting rules already decided, with the depth of the tree already decided by someone, and we are just using it to make inferences. But now the question is, how can we train a tree ourselves? How can we construct this tree based on the training data? Note that training a tree can also be said as growing a tree. It's the same thing. So to grow a tree, we need to establish the splitting rules of each node, and also how many nodes we want, and also the label that we want to associate to each node. So let's start with this last problem. Let's first understand how to associate a label to each node. So this is quite easy. So we construct a histogram for each node. So we let all the training samples cross our tree, and for instance, if we focus on the first node, we count how many samples that passed through this node were home and how many were work. Okay, and we repeat the same here in all the nodes. So for instance, in this node, there are more more work samples that pass by and less home samples, while on the right we have more home samples and less work samples. So we can of course assign to each node the label of the prevalent class. So in this node we have more home samples, so we will assign the label home to that node. And we do the same for each node. So at the end, we have our labeled tree. So I repeat, we associate to each node the prevalent class. Now let's decide the splitting rule. Okay? And first, let's take some moment to understand how to compare if a rule is better than another. So suppose you have this dataset here. Okay, it is exactly this dataset, the same dataset on the left and on the right, where the samples are, the features are age and time, and home samples are red and work samples are blue. So if we use this splitting rule here, time less than 8 AM, we will divide our dataset in this way. While if we use age less than 80, we will divide the dataset in this way. So, which splitting rule, in your opinion, is better? Well, we observe that the splitting rule on the left is not so good, because each of the subsets that we have created are still a bit confused. There is a lot of impurity. So here in the subset, in the upper subset, we have many blue samples and also many red samples, and the same for the subset, the subset in the bottom. Okay, so if we compute the histograms of the left node, and of the right node, these histograms will not show a really prevalent class. Okay, there will not be a clear prevalent class. While if we go and check the rule on the right, it is a bit better, because at least this subset here on the right, this B, is pure, let's say. There is a clear prevalent class, the red class. Okay? So in general, we should prefer rules that create pure subsets, because a classification task is something that allows you to discern, to organize your samples and to discern which ones are red and which ones are blue. So the purer are the subsets that you obtain after splitting, the better. So this is understandable by intuition, but we need a mathematical way to express this thing in order then to construct an automatic algorithm that can decide itself the best splitting rule to grow our tree. And there are two metrics that we can use, entropy or Gini impurity. Let's see first the entropy. So the entropy is a concept that exists in chemistry and also in information science. And actually it took inspiration from these fields. So we have again blue samples and red samples. Okay, we denote with P blue the if you take a certain set of samples, they can be blue and red, we denote with P blue the fraction of samples that are blue in that set, while PR is the fraction of samples that are red. So for instance, if we consider the set A, P blue is 1, P red is 0. If we consider set C, P blue is 3 over 6, P red is 3 over 6 as well. So with this in mind, we can compute the entropy. The entropy of a generic subset is this formula here, is the probability of blue times the logarithm of 1 over probability of 2 plus the same thing for the red. So let's, to understand this formula, let's just make an example. So let's compute the entropy of this set A. Well, probability of blue is 1. Okay, so logarithm of 1 over probability of blue is logarithm of 1, which is 0. So this whole term is 0. And probability of red is also 0. So the entropy of this set is actually 0. So if we compute the entropy of this set, it will also be 0. So when a set is completely pure, so there is just one class, the entropy is 0. So entropy, small entropy means pureness. Let's compute the entropy of C. So the entropy of C is probability of blue, that is 0, that is in other terms 1.2, 1 over 2, times logarithm of 2 plus the same thing for the red, because we have half red, half blue. So 1 over 2 logarithm of 2. If we compute this thing, this is logarithm of 2 is 1. Okay, so we have 1 over 2 plus 1 over 2. So result is 1. This is the maximum entropy we can have. Maximum entropy. And corresponds to the case where we have maximum confusion. So we don't have a clear prevalent class, because more or less we have as many blues as the number of reds. So in this case, the entropy is the maximal, and the value of entropy is 1. You can compute yourself the entropy of D and of E. Of course, you will find that the entropy of E is smaller than the entropy of D, because in E there is less confusion. It's more clear that the prevalent class is red, while in D there is still a bit of confusion. So there is a bit of mixity, a bit of impurity. So less impurity than C for sure, but still the prevalent class is the blue, but it's not that clear. So the entropy in this case, D, is somewhat high, almost 1. Okay? So the same formula can be extended in case we have more than 2 classes with no difference at all. So we understood the entropy. Now let's understand the information gain concept. So suppose we have this entire data set and we can compute the entropy of this entire set of points, as we did before. Now let's try to separate them into subsets, A and B. And let's compute again the entropy of A and the entropy of B. So we can define the entropy of the split as the average of the entropy of the 2 subsets weighted by the amount of samples of set A and of set B. So the bigger set after the split, the bigger subset, sorry, will correspond, will have a higher weight in the computation of this average here. So I repeat, the entropy of a split is the weighted average of the entropy of the resulting subsets. So it can be shown that whatever split you do, the entropy of the split is always less than or equal than the entropy of the original entire set. This is intuitively understandable because every time you divide a set in 2 parts, you are making some sort of, you are removing some confusion, at least. You are organizing your samples anyways. So every time you divide, you split a set, you decrease the entropy. So in other words, you are gaining some information. So this is why we define the information gain as the difference between the entropy you had before the split and after the split. So the quality of a split is given by this information gain. The more is the information gain, the more you are succeeding in reducing the entropy. So you are creating more order in your data set. So when you want to compare different splitting rules, you have to prefer the one that gives you the best information gain. So let's come back to our example. So if we compute the information gain of this splitting rule, it will be way less than the information gain of the splitting rule on the right. Because here the entropy of A is quite high, and here the entropy of B is quite high as well. While on the right, the entropy of A is still high, it's okay. But the entropy of B, at least, is way small. We can then apply the same rule recursively to train the entire tree. So we start with the root node and we decide to take the splitting rule that gives us the maximum information gain. Then we check the other possible splits. So we check a split in the node on the left or a split in the node on the right, and we always select the split that gives us the maximum information gain. So this is the basic concept of CART. Okay, so CART algorithm means classification and regression tree. actually is an algorithm to decide what should be the splitting rule every time. So first, to apply a cart, we need to decide the splitting points for each feature. For instance, we may decide that age has 30, 40, 50, 60, 80 as splitting points. So these numbers will be considered by our algorithms to form a splitting rule. And we do the same for all the features, duration, etc. Then at each iteration, for each node, we compare all the possible splitting rules. And we compute the information gain for all the possible splitting rules. So for instance, we compute the information gain of age less than 30. Suppose it's 0.3. Then age less than 40. Then the information gain of duration less than 2, duration less than 4, and so on and so forth. So we have then all the splitting rules that we may apply in this first node together with their information gain. And we select the one with the highest information gain. Suppose it is age less than 80. Then we reason on the node on the left. And again, we compare all the possible splitting rules. And we decide another splitting rule here. We do the same for the node on the right, etc., etc. This is how, at the end, we will have a complete tree with all the splitting rules. And then we add the label that is just the prevalent class of each node. This we have seen it before. An alternative to the entropy is using gene impurity, which is computed as this. So if we take a set S and we have k classes, the impurity of this set is this sum here. So the fraction of samples of that set that is of class k times 1 minus this probability. For instance, here we have just two classes, red and blue. And if we compute the impurity of this set, we will have p of red is equal to 1 times 1 minus 1, 0. And then p of blue equal to 0 in this set multiplied by 1. That is always 0. So the impurity of this set is 0. If instead we take this other set, I let you compute yourself that the impurity is 0.5. So the impurity is 0 when we have just one class in our set. And so the set is pure. So the impurity is 0. While the impurity has its maximum value that corresponds to 0.5 when the set is maximally confused, let's say. There is no prevalent class, equal number of samples per class. So conceptually the impurity is the same as the entropy. What changes is the number itself and the range that is from 0 to 0.5. Similarly to before, when we have a certain set and we split it into two parts, we can compute the impurity of this split, which is the weighted average of the impurity of each resulting subset. Okay? So we can compute exactly the same CART algorithm using gene impurity instead of entropy and information gain, but nothing changes. So when you write your decision tree in Python, you have to decide this hyperparameter, either to use gene impurity or entropy. There are also others, but we will not see them. This figure I think is nice because it lets you understand what is the relation between the depth of the tree and the way in which we are partitioning your feature space. So this figure here corresponds to a tree with just one split, where the node on the left corresponds to the bottom part, the node on the right, the upper part. These figure on the right corresponds to a tree of depth 2, where we divide the node on the left in other two parts, and so we have these and these correspondence, and the node on the right also in two parts, which corresponds to this region and this region. Okay. And if we increase the depth of the tree, we will make decision boundaries that are more and more complicated. So we can grow the tree up to its maximal depth. That is when you reach a point in which in each node you have just one class. Okay? In this case, you will say that your tree is fully grown. So this is an example of a fully grown tree. Okay, you have just one sample per each node, and you can't split any node anymore. So you stop. Having a fully grown tree is not a good idea because it is prone to overfitting. Because your tree will be able to do crazy stuff like this. It will be able to create a region of the space just for a single sample. And maybe this sample is just, an exception. So it would have been better to just take the entire region that I'm pointing at as a blue region, instead of creating a sub-region for just one red point. Okay? So you should never use fully grown trees, because they almost surely will overfit your data. So which is the depth of the tree that you should decide? Well, this is a hyperparameter that you should choose and you should experiment with. But there are some heuristics that you can use to decide this parameter. And the most used one is pre-pruning. That means to stop growing your tree, stop creating new splitting rules early, so before having a fully grown tree. And the criteria to do so can be different. For instance, you may decide that after all your nodes have less than a certain threshold of samples, you stop. Or you may decide to stop when any new splitting that you do doesn't provide enough information gain. Or you may decide to stop if a certain number of nodes has been already reached. So this is what you will likely use in your Python code. You will see that you can also combine these criteria by just specifying all these hyperparameters in your code. Now that you know enough about trees, I have to tell you that trees are never used in practice because they suffer high variance, so they are practically unusable. So let's see where this problem comes from and how to correct it. So let's first recall the definition of high variance for a model. So we say that a model suffers high variance when we perturb a bit the training dataset, the model changes completely. A model with high variance is not good because its decisions are driven by the details of the dataset. So the model is not stable. It is not learning the important information contained in your dataset. So let's see why in trees this happens. So suppose we have the scenario of the activity classification, and we thus want to train our tree and we want to decide our first splitting rule from the root of our tree. So we compute the information gain with different rules. For instance, we compute the information gain of age less than 80, and suppose it is 0.1002. And information gain of time less than 8 a.m. and suppose, it is 0.1000. So they are very close to each other. If you run the CART algorithm that you have seen, the first rule will be selected, age less than 80, because the information gain is more. And then we will continue to grow the tree from that point. But observe that the information gain of the two rules is very close. So maybe if we just have an additional sample in our dataset, maybe the information gain would be a different one. So maybe this time the second rule would have an information gain slightly bigger than the first rule. And so we would grow a tree completely different. So look at this. So in the first case, we would have a tree that grows like this one on the left, and then just by adding one sample only, we may grow a completely different tree. So this is showing you that just a small detail in your dataset is changing completely the model that you have at the end. So the model is not stable. It suffers high variance. How can we solve this? Well, we solve it through ensembles, by combining different trees together. So let's take an example in real life. Suppose you're the president of France and you have to face a pandemic. Okay, what should you do? You have two choices. You can call the best expert in the world and follow his advices, or you can call 10 experts. Maybe they are not the best in the world, maybe they are just okay, but they are 10. Which one would you prefer? Well, it is for sure preferable to have 10 good experts instead of just one excellent expert, because nobody is perfect. So even the best expert in the world may be wrong. So if you just follow the suggestions of one person, even if this person is excellent, you risk to take wrong decisions. So this is telling you that it is always better to prefer plurality when you take decisions. Okay, so this is also why democracy is preferred in many countries to dictatorship. Okay? We have many people working together to arrive to decisions. And we do the same with trees. So instead of just using one tree for making a prediction, we grow several trees together, independently, sorry, and then when a new sample comes, we let each and every tree do its prediction, and at the end we combine these predictions together. There are actually 4 main approaches to do so. Let's start with the simplest, bagging. So in bagging, we first take our training dataset and we divide it in k subsets that may also be of different sizes. And then we grow a separate tree for each subset. So now we have several trees that are being trained on different subsets. So they may be very different. Okay? Now a new sample comes, and then you submit this sample to tree number 1 and you get a prediction. Tree number 2 and you get a prediction, etc., etc. At the end, the class you will choose is the most voted. Okay, so you do majority voting. So you label the new sample with the class that most of the trees have predicted. Observe that by doing this, you also have more interpretable results, because if you have a sample and all the trees say that this sample is red, you have high confidence that the classification is correct. While if, for example, for a new sample, 40% of trees say it is blue and 60% say it is red, well, you may have a confidence with 60% that your sample is actually read. So ensemble learning also increases generally interpretability of your results. This is bugging. Random trees are just a modification of, random forest is just a modification of bugging. So let's see what is a problem of bugging first. So in bugging, actually, most of the times you will have very similar predictors. It's true that these predictors are grown on different datasets, but at least in their upper part, they most of the time look similar. So you will end up with learners with predictors that will almost say always the same thing. So it is not interesting for you to have many trees that give the same classification, because it's like having just one. So if in the parliament all the deputies always vote the same thing, and it means you're not exploiting in the best way possible the plurality of your voices. So in random forest, we instead try to have diverse trees. How can we do so? So in addition to separate the training set in different subsets, we also, when we select the best splitting rule for each tree, we don't consider all the features, but we consider just a subset of them. So usually if you have n features in total in your dataset, every time you have to choose a splitting rule, you just look at square root of n features that you select randomly among the n features in total. So what you are doing is that you are adding more randomness to the generation of your trees. And so at the end you will have more diverse trees. Okay, so this is an important point in general in machine learning. The most you give randomness to your model, the most you insert randomness in the generation of your model, the better. And in particular, this is true for ensemble models in which you have different learners and you want to make them as different as possible. So this is a plot that is showing you how the error in the test set keeps decreasing if you add more trees. So the more trees in your ensemble, the better. This is always true. So when you add more trees, you are not actually adding more complexity to the model. So if you go back to neural networks, when we add more neurons or more layers, we are making our approximation function more flexible. And this had the risk to overfit our data. So we were making our model more and more complex if we add more neurons, and so we were risking overfitting. This risk is not there with random trees, with random forest, because adding more trees to your forest is not increasing the complexity. Each tree is complex the same. You just increase plurality and you just increase randomness in your ensemble, which is always good. So this is an advantage of forests with respect to neural networks. So the only limit to the number of trees you should add to your model is just computation capability. A nice thing that is possible with random forest is, and also with actually bugging, is interpretability. Okay, because you can have an idea of confidence in your prediction, and I've already commented this. Here I'm just showing you the same concept with the figure. So in this column here, we see all the decision boundaries of some decision tree, just one tree. And we see that the decision boundaries are just lines, of course. While when we have a random forest, we may say that we use a color intense red when all the trees predict the class red, while we decrease the color when a percentage of trees predict red and another percentage blue. So here you can notice that all these points here are classified as red, and we have high confidence that their true class is red. While for this point here, they are also classified as red, but we have less confidence in this. So when a random forest gives us a result, we may also understand if we should trust or how much we should trust this result. We will skip this. So finally, extra trees are a modification of random forest. This is incorrect. This is forest. Okay, are a modification of random forest where instead of applying the cart algorithm, so instead of always choosing the best splitting rule that provides the highest information gain, we instead select a rule randomly. It can also be a bad rule. It doesn't matter. We select the rule when we grow our tree completely random. So why it is good? Because again, we are even since we have many trees, if each of them is not that great, it doesn't matter, because at the end the plurality will compensate for it. So by adding this other element of randomness, we are making our trees more diverse, and so usually extra trees have better results than random forests. So going from single trees to extra trees, we are increasing randomness. First, with bugging, the randomness was just due to the fact that each tree was grown on a different subset of the training set, and the subset was thrown randomly. With random forest, the randomness also came from the fact that you don't consider all the features when you have to choose the splitting rule, but just a subset of features, and the subset is generated randomly. With extra trees, you also add the fact that the splitting rule that you always choose is not the best one, but is a random one. An improvement of ensemble methods is boosting, that we will not see, but just to I want to give you the idea, and is that bugging random forests and extra trees grow trees independently. Okay, so each tree is grown without looking at the other. While in boosting, while you train a tree, it is trying to correct the weakness or the errors that the other previously trained trees have committed. So, and usually boosting gets better results. Actually, one famous implementation of boosting is XGBoost. That has, like with this method, people have won a lot of competitions. So we have seen that with ensemble method, we gain in interpretability because we have an idea of confidence we have in the results. We also can have the an interpretability in the sense that we can understand what are the most important features. And in fact, we can use an algorithm like this. So we grow a set of trees in bugging or random forests or extra forest, and then we want to understand the importance of a certain feature. Well, what we do is that we check all the rules in which that feature is used in all the trees. Okay, and we check what is the information gain that we obtain each time this rule was applied. And we sum all these gains. Okay? We do this for all the features. And then we normalize in order to have a number that is, in order that the sum of the importance of all the features is 1. Okay? What you obtain is that the features that have a higher score are the most important because they have allowed most of the information gain while training your trees. So the plot that you get is something like this. So in this particular data set, this feature was the most important. So it was giving most of the information gain while training the different trees of the ensemble. We will also see how to obtain a similar plot in Python. Okay, you may be able already to answer to this question. So, is scaling needed with trees? Actually, the answer is not, because anyways, when we select a splitting rule, the algorithm will see always the range of all the features, and the splitting points will be somewhere in this range. So if this range is small or is high, it doesn't matter at all. Observe that so far we have considered ensembles made of the same kind of models. For instance, we have considered ensembles of trees, but you may also have ensembles of different models. You can put together trees, neural networks, logistic regressors, etc. These kind of ensembles are called, this kind of approach is called blended learning, and it has shown good results in all the data science challenges. Even if you will not study it, you're welcome to try it out on your dataset if you want. Before going to the code, I want just to tell you that we can use trees also for performing regression. So far we have just seen classification, but regression is very similar. So if you grow a certain tree like this, where each node corresponds to a region of the feature space, well, you associate to each node a label. In a regression, a label is a numerical value, and this is just the average of the samples that are inside that node. So the rest is similar. Also, when you decide the splitting rules, you don't look at the information gain because it doesn't make sense in regression, but you select the rule that minimizes the mean squared error in your resulting subsets. The code to run random forests is in the file 5.treesandEnsembles that you can find in my GitHub. We will in particular use random forest classifier from scikit-learn library. Let's jump directly to the description of the use case. We are going to use Google cluster traces. These traces represent 29 days of activity in a Google cluster. In a cluster, users submit tasks, and each task has certain requirements in terms of CPU demanded and memory and disk, etc. And also in this trace you find also the available resources at submission time and other information. And then the most important column is the violation. This is one if the task was evicted before termination. This can happen when, for example, there are not enough resources available at a certain point of its execution. While this column is 0 if the task terminated correctly. So the goal of this notebook is to predict in advance if a certain task is going to be evicted or not. Because if it is the case, we can raise a warning to the user so that the user can adjust the requirements of his task, or it can submit it later. So here we load the datasets. We observe immediately that there are some columns that we cannot use because they are not informative to determine the destiny of a task. So unnamed 0, we don't even know what it is, so we will not use it. Job ID and task ID are not useful, while all the other things are useful. Here the class of a task indicates whether it is a time-sensitive task, or if it is a production task or a development task, etc. Then we have the priority, the amount of CPU requested, the memory requested, and the disk. And finally, this violation. Observe that memory, CPUs, and disk are expressed in a strange way. So they are not expressed with the usual unity of measurements. This is because Google wanted to obfuscate the information about its clusters for security reasons. So they normalized their datasets. So this is not interesting for us. You can check how they normalize the dataset in their description, but we know anyways that this memory requested here, for example, is proportional to the actual memory requested by that task. Here I put the description of the single columns. So we are eliminating the columns that we cannot use, and this is the dataset with which we are going to work. We have in total 201,000 rows. Okay. So we first verify that we have an unbalanced dataset, because fortunately most of the tasks terminated correctly. So before training any model, we do synthetic minority oversampling technique to avoid any class imbalance problem. And we saw this in the previous notebooks. Now we will build our classifier. So here we are telling that we want 100 trees inside our forest, and that we want to use gene impurity as metrics. We also established that we want at most 16 leaf nodes. So after we have obtained in each tree 16 terminal nodes, we don't want to add any other splitting rule. So this is to limit overfitting, as we've seen in the slides. And then, okay, the number of features to consider at each splitting rule is left as default, so the square root of the total number of features. And then we first train the model, and we check the performance on the test set. Here I'm representing the confusion matrix, and we see already that our confusion matrix looks quite good from the beginning, and we are quite happy with that. As we have seen in the slides, with random forest we can also have an idea of how important each feature is, based on the amount of information gained that it provided us during training of all the trees. And I created a function for you that you can find in one of my libraries. We imported this library at the beginning of this notebook, and you can reuse this function right away. It's very simple. You code this line and it gives you this kind of plot. Observe that the most important feature that determines whether a task will be evicted or not is memory requested. And then we have disk requested, and then the other columns. So this is already giving us an important information. So we know that if we want to limit the probability of being evicted, we have to request less memory. And this is something we would expect. Now, we started already from a good baseline, a good random classifier with good performance. But let's check if we can still improve. So we will now check different hyperparameters. So instead of using just Gini impurity, we will use also entropy. And then we will also, instead of using max features as the square root of the total number of features, we will try different values. And we will also try different number of leaf nodes, etc. So in theory, we would like to make a grid search, trying out all the possible combination of hyperparameters. But you see that there are a lot, so it's very difficult to do grid search in this case. So we will choose another approach, that is randomized search. In randomized search, we are telling that we just want to test 50 possible combinations of hyperparameters among all the possible ones. This is what we do. Here I did a mistake, because here I should fit my randomized search on the training set. I should only use the training set to find the right hyperparameters. Okay, so this is wrong. Here I should have written X train. I will correct it. And we plot again the confusion matrix. So you may notice in your dataset that sometimes after you do randomized search or other techniques to improve the model, you may end up with the model that is worse than the initial one. So this is to tell you that don't start immediately by tuning the hyperparameters. So first try to train a model with hyperparameters that look reasonable to you. At least do it at the beginning. So you have a good a baseline, hopefully good enough, that and then you can improve upon it. So don't start directly looking for all the combinations, start with the reasonable combination first. Another thing I want to show you is that, as we did for neural networks, we can also store a random classifier in a file. Here I'm storing it in a folder in my Google Drive account that I mounted at the beginning of this notebook. You can check it in the previous lines. And then you can load the model later, already trained. Okay, so you don't have to train it again every time. Here I'm just writing a function. I suggest you to do the same, where I want the following. So instead of directly creating a model, I use this function here. Actually, I give the file name in which the model has to be saved, and I'm saying that if the model already exists, you don't have to do anything, you just load the model. Otherwise, you can do randomized search and immediately after you finish, save the model, dump the model, so that I can reload it later. So by using this function, I don't have to check every time, or do I have already a model that I trained before or not. I mean, I just use this function and it will take care of checking whether the model exists already and has already been trained, or if you have to create a new one. Here I'm trying to improve my model by just checking more combinations of hyperparameters, not 50 but 200. And I'm improving a bit, but still the first model we had is the best. Of course, you have different ways of still improving the model. For instance, you could use extra trees instead of random forests, or XGBoost. Or also, a safe way to do it is to just increase the number of trees, because we have seen the more trees you have, the better your model. Of course, you're limited just by the computational power you have. That's all for this lesson. Today we have seen tree-based learning. We started with a single tree and we understood how to train it using CART algorithm. Training a tree means to grow a tree, to start from a node and create children of these nodes. And we saw that the criterion to grow a tree is actually the impurity measure. We have two impurity measures, gene impurity or entropy. And when deciding how to create additional nodes, we always chose the splitting rule that maximized the information gain. We then observed that the decision tree suffers high variance. And a way to correct this is to resort to ensemble learning. That means to put all together different trees trained independently. And then when a new sample comes, you let these trees make their prediction independently, and you choose the most voted prediction. Okay? One advantage of tree-based learning is its high interpretability, because we can have a result and we can also have an idea of the confidence on these results. Because if a certain class was predicted by 90% of trees, we can have high confidence that that class is the correct one. While if it was predicted by just 55% of trees, our confidence should be less. Moreover, we also have an idea of the most important features in our datasets that correspond to the ones that provided most of the information gain while training these trees. In next lesson, we will instead talk about unsupervised learning, and in particular clustering, and how to make anomaly detection.